So I filled in this table. I thought it would be good for you guys to include this in your notes. We have our three problems here. The problem of too many electrons. So if you have an atom over here, remember we're going to be going through alpha decay. If we have too many neutrons and not enough protons, we're going to have an atom over here, and that will want to go through beta decay. And then if we have an atom in this area, we'll have too many protons, not enough neutrons to hold them together. And those atoms can either go through positron emission or electron capture, either one of those. So that would probably be a good thing to stick in your notes. Another thing I want to go over. So another theme that's coming up right now that we're going to discuss multiple times throughout this chemistry class is that everything in the natural world is lazy and wants to find stability. And when I say stability, I'm talking about its lowest energy state, or it's going to use the lowest amount of energy to exist. So when we think about atoms, when an atom is unstable, it takes a lot of energy for that atom to be unstable. So over time, it's going to want to become stable. It's going to want to go through radioactive decay to become stable, because that is a lower energy state. So that's why it happens. And some unstable atoms, when they're extremely unstable, they might go through radioactive decay in a matter of nanoseconds or seconds, whereas some atoms might be less unstable. It might take years to go through radioactive decay. And then some atoms, even like bismuth, is just slightly unstable, and it might take billions of years for that to go through radioactive decay. So it depends on how high of an energy state or how unstable that atom is to determine how quickly it will go through radioactive decay. All right, to finish up radiation, I want to talk about this table that you can write in your notebook. It goes over each type of radioactive decay and includes something we haven't talked about yet, gamma emissions. We can see with alpha decay, the particle that's emitted, the change in our mass number would be a decrease of 4 because we are emitting 2 neutrons and 2 protons. And our change in atomic number would be a decrease in 2 because we are emitting 2 protons. We got beta decay, which is you're emitting a high energy electron. No change in mass number because it's just an electron. And we have an increase of atomic number by 1 because a neutron is becoming a proton. For a positron emission, we got a positron, or a positively charged electron, you could think of it as, being emitted. No change because remember it's very, very small mass, so the mass number is not changing. And that would be a decrease in our atomic number because the proton is becoming a neutron. We got electron capture, which it's capturing an electron, so it's only emitting electromagnetic radiation, or we could think of it as X-rays or gamma rays. No change in mass because these have no mass. And it's a decrease in atomic number by 1 because the proton is becoming a neutron. And then lastly, I want to talk about gamma emission or gamma rays. And we briefly covered earlier that unstable atoms are at a high energy state, and when they become stable, they're at a lower energy state. So that energy has to go somewhere. So in addition to emitting particles, oftentimes certain amounts of energy are emitted as well, and that would be in gamma emission or other ionizing waves such as X-rays or high frequency UV rays. But we're just going to talk about gamma emission here. So the last thing I want to talk about is protecting yourself from radiation. So alpha decay, this particle has the largest mass. So alpha decay actually doesn't even get past your skin, and it could be blocked with something as thin as paper. So blocked by paper. So that's how you could think of that. Whereas beta decay and positron emission, these are much, much smaller, so they can penetrate things much farther. So depending on how much energy that electron or positron has, you might need, very thick clothing to block it, or even some lead. So we can put here blocked by thick clothing, and we'll put a line in between this one, and this will be true to both these. Thick clothing, you know, a little bit of lead, or, you know, concrete. So this could be blocked, think like by the walls in your house, or by the, like really, really thick clothing in some cases. And then we have X-rays and gamma rays. So the more high frequency or the higher energy your rays have, the farther they're going to penetrate. And these have no mass at all, so they can go significantly farther. So think of like a bunker where you have several feet of lead, or several feet of cement to block these radiations. So several feet, sometimes 20 or more feet of concrete or lead. So these can go through a lot more things. For x-rays, an example I like to use is when you go to the dentist, they take x-rays of your teeth and they put on that lead vest, that heavy lead vest, to help protect your body from those x-rays. So in that case, a little bit of lead is blocking those x-rays. So I want to think of these as the penetration increases as we go down. So alpha decay, or alpha particles, will have the least amount of penetration because they can just be blocked by a small piece of paper. Beta decay and positron emission, those beta particles can go a little bit farther through things. And then our gamma emission and our x-rays can go significantly farther through things. So we have increasing penetration as we go down this table.